Hi, everybody. Thanks for making it in the last day so early. I will talk about the structure of solutions to pseudo-random constraint satisfaction problems. So let me start by defining what I mean by a constraint satisfaction problem. Throughout the talk, we're going to be looking into problems where we have n variables, all of which have the same small discrete domains. So oftentimes this domain is going to be just two values. And upon these variables, there's m constraints that are acting. And each constraint favors a subset of all possible configurations of the variables that it binds. And the degree of each constraint is always going to be constant. So each constraint is going to bind maybe 2 or 3 or just a handful in general of variables. And to the extent that I sort of draw this graphically, I'm going to be using this Tanner graph notation. Now, just to familiarize this notation with things we already know, if you look at the graph K coloring problem, we put the vertices of the graph on the left, and we think of them as variables that have domain 1 up to K, the K colors that are available. And then each edge in the graph is a constraint that takes 2 of the variables and says that the value of these 2 variables should just be not equal. Anything else is okay. And another problem I'll talk about a fair bit in the talk is the K-SAT problem. So here, the variables are Boolean rather than being K-ary, and the constraints are K-ary rather than being Boolean. So each constraint is a clause, and a clause is just the logical OR of a subset of variables or their negations. So basically, a clause of length K binds K variables, and out of the 2 to the K possible values, it forbids 1. And we want, of course, all the clauses to be simultaneously satisfiable. So this is sort of the only sort of somehow high-level, perhaps, slide in the talk. So we have these objects that have polynomially short descriptions. For example, there's factor graph representations. And each constraint typically forbids a constant fraction of the set of all possible values. And then what essentially I think we're trying to figure out is whether the set of values that remain as candidate solutions is empty or not. And obviously, if we were allowed to remove candidate solutions one by one out of, let's say, 2 to the n possible solutions, we could easily create a very difficult problem. The problem would be then, though, that the representation would be exponentially long. So one can think of the P versus NP question as saying, you know, I have this cube in the case of satisfiability, and I take huge subcubes, and I sort of bombard my original cube with it, and eventually I'm left with some kind of shape. And now the question is it possible to distinguish the remaining set from the empty set in polynomial time? So the reason we're looking at random constraint satisfaction problems is because you can think of randomness as some kind of source of approximate uniformity. We would like to bombard each part of the cube kind of equally, and we use randomness to try to achieve this in an unstructured way. So just to give 2 concrete examples of random CSP. Well, actually, before doing that, so the general setting is going to be that each constraint, the sense in which the constraints are going to be random is that each constraint picks a random subset of the variables to bind. So there is absolutely no geometric structure in which variables interact. So another way of saying the same thing is that this graph is going to be a random bipartite graph in which typically the right-hand side is going to be the regular, and then if we leave the other side to be completely free, it's just a balls and bins experiment, so it looks like Poisson degrees. As you all know, this random bipartite graph is an inherently high-dimensional object. So we can't really hope to have small separators, for example, that would allow us to decompose the problem. And this is one source of hardness for these instances. Another way of perhaps saying the same thing is that these instances are going to be sparse. So throughout the talk, the number of constraints m is going to be linear in the number of variables n, and I'm going to use this quantity r for the ratio of constraints to variables, sort of irrespective of what problem I'm talking about. So the point is, if you take any such random bipartite graph and you take any particular vertex that you like and you do breadth-first search from that vertex, then at any finite depth you go, you're going to see a tree. Maybe there'll be one more edge, but basically it's a tree. Which means, for example, if you're trying to do graph coloring, locally from the point of view of every vertex, the graph actually looks bipartite, whereas in reality, you need a lot more colors. The point being that the reason that you need a lot of colors has to do with long-range influence that is being exerted on the boundary of this tree from the rest of the structure. Finally, just a technical point. We can also make these instances be biregular. So for example, if you wanted to look into the coloring of random regular graphs, what you make sure is that each edge of the graph, when you sort of, as a half edge, when you throw it from the right side to the left, rather than having it land in a uniformly random bin, in a uniformly random variable, you just make sure that you hit each variable an equal number of times. This is known as the configuration model. And you can actually prescribe any degree sequence that you like if you think that this is important. In this talk, I'm just going to basically have the degree sequence be Poisson, so there's not going to be any restriction, and this gives us some slight technical advantage. So, like I said, this is what happened. This is a way to represent random graph K coloring. You have the n vertices in the graph, and then each edge simply picks two of the variables at random and says these two variables must take different colors. And you can do random R-regular graphs, like I said, again, by making sure that each vertex on the left eventually acquires the same degree. For satisfiability, it's sort of the same trick. If you want to create a random KCNF, you look at all n choose k possible ways you can choose the variables, and then for each variable, there's 2 to the k possible ways in which you can negate the literals in it. You take all these possible constraints, you put them in a bag, and then you draw from that bag. And this bag is going to have size maybe quadratic or cubic in n. So we only draw a linear number of objects, so it doesn't really matter whether you do it with replacement or without replacement. And then in this picture, every constraint, that is every vertex on the right, has degree k, and I use white and red just to denote whether this particular variable we want it to be negated or not in the constraint. And in exactly the same fashion, one can model a bunch of different NP-complete problems. So not all equal KSAT is one that we will see in a second. So in satisfiability, in a KCNF, we're seeking an assignment of values to the variable such that every clause has at least one true literal. In not all equal, we demand that we find an assignment in such that in every clause there is both a true and a false literal, which is basically the same thing as saying that we're looking for complementary pairs of satisfying assignments. And then you can look at hypergraph 2 coloring and vertex cover on random instances and so on. And pretty much everything I will say today in the technical sense goes through uniformly for these problems. So here's a theorem which demonstrates that in some aspects, we have significant control over such structures. It basically says that if you have a random graph with bounded average degree, we essentially know what its chromatic number is up to 1. So as an example, if you tell me that the ratio of edges to vertices is 6.73, then with probability that tends to 1 as n tends to infinity, the chromatic number is 5 or 6. If the ratio is 10 to the 60, then the chromatic number is either this integer or the next. So we really know how many colors it takes to color a random graph. But as we will see, it's significantly harder to find, or at least we don't know how to find colorings with so few colors. So concretely, here is an incredibly naive algorithm. And basically what this algorithm does is it hardly looks at the input. It takes a random vertex, it assigns it a random color, and the only time it does anything intelligent is if at some point there is a vertex such that k minus 1 distinct colors have already been occupied by its neighbors, then we give that vertex priority and we assign it the last possible remaining color for it. But that's it. So we only do things at the very last possible, meaning no planning, no global look at the graph, nothing. And then we know now for quite a while that this algorithm will find around a k coloring in a graph when the density is about half of what we know is possible. So we know that if you have k colors available to you, you can color random graphs for densities up to about k log k. This simple algorithm will find a solution for densities up to half that. And what's remarkable is that all known polynomial time algorithms fail if you try to improve this. And by fail, I don't mean that we necessarily have a proof for every one of them, but there isn't even a candidate which experimentally does well. And it's not that the problem is with our capacity to analyze them. There isn't a candidate right now which can beat this factor of 1/2. And then for satisfiability, the following conjecture has been around for a while, that basically for every k greater or equal to 3, there exists some critical density such that the probability that a random formula is satisfiable goes from near 1 to near 0 around that density. So you see this plot here for the case k equals 3, and the plot gets closer and closer to a step function as we increase the number of variables. So if this constant exists, one can prove in basically one line that it's not more than this. And maybe in half a page, one can prove something like 2 to the k over k times 1/3. And maybe in 2 pages, you can improve 1/3 to 1, and so on and so forth. But for a while, it didn't seem like it was possible to get a significant improvement over this, maybe perhaps up to something like log k, and this was done last year. So basically, we know how to find solutions in random KCNF formulas for densities up to this. We know that solutions do not exist for densities higher than that. And in between, for a while at least, we didn't know what was going on. Whether solutions exist and algorithms can't find them, or it's the upper bound that's the problem. So by now, we know that actually solutions exist almost all the way to the upper bound. So for example, if k is 10, we know that if the density of the formula is above 709, there are no solution. If it's below 704, there definitely exists solution. But all algorithms that we know break down at something like 173. Now, this phenomenon that I described for coloring and SAT, hold on. Seems to be quite generic. So you get a similar phenomenology for a bunch of other random constraint satisfaction problems. And the way it looks like is that it's easy to get some kind of an upper bound. And the upper bounds you usually get by simply saying, I'll take the union bound over the set of solutions of the probability that a fixed value assignment is actually a solution. You take the union bound, and this gives you an upper bound, typically very, very fast. Like I said, you let x be the number of possible solutions. Sorry, you let x be the random variable, which is equal to the number of solutions. And this is typically a continuous function in the density. So at some point, this expectation hits 1. And then to the right of this density, you can show that with the probability there is any solution is exponentially small. Note that the fact that there are solutions to the left of these, that this expectation is exponential to the left of this density doesn't necessarily imply the existence of solutions, because this exponentially large expectation could be due to relatively rare formula. So we could have some kind of a lottery phenomenon. Now, similarly to the easy upper bound, one can analyze often some naive algorithm that gives a faraway lower bound. And if you work harder, You can analyze something which is a bit more sophisticated, but in all these cases, it seems to be that we're hitting some kind of a law of diminishing returns. So the paper gets longer and the improvement gets shorter. So, and then it seems that for all these problems, we can get non-algorithmic lower bounds. So we can prove the existence of solutions for densities that essentially match the upper bound density. So at this point, we have a very good sense of when the problems stop being satisfiable. But this is done, like I said, in sort of with an existential kind of proof, which is essentially a concentration argument. What we do is we prove that this random variable x is actually typically very close to its expectation, and as we saw, the expectation is exponentially large. Concretely, we do this using the so-called second moment method, and I'll just give you a quick walkthrough of how the second moment works in random constraint satisfaction problems, but if you don't follow this part, that's fine. I just added it last night. So let S, for an instance, let script S be the random variable equal to the set of all solutions for that particular instance. So the first step is to identify some appropriate subset of the set of solutions. And oftentimes, this identification is trivial. We just take all solutions. But other times, you actually have to be a bit more clever. And then you say, let x be the random variable which is equal to the number of solutions. And then we prove concentration, in some sense, in the weakest possible form. We show that the second moment of x is big O of the square of the expectation. And that's good enough for our purposes. Now, this is a high-level view of the second moment computation, and I think it's sort of worth walking through it because it highlights a couple of things that I think are important for future work. So in the first line, it is just a substitution. So what's inside the brackets is just x. So x is the sum over all possible, I don't know if is there a laser pointer? It doesn't matter. It's the sum over all possible value assignments sigma. And then we have a product over the set of random constraints C of a function f, which is typically an indicator function. It basically tells us whether C is happy with sigma. So for example, if we wanted to count the number of satisfying assignments in a case C and F would be the indicator that clause C is satisfied by value assignment sigma. So that's just the first line. But sometimes F also encodes this selection of script C. So it is not just an indicator of satisfiability, but also perhaps explores this thinning that we're doing of the set of solutions. So now you open up this so you open up the square, you push the expectation through. You know, this pushing is trivial, but for this pushing, we exploit the fact that our constraints are independent. That's the second line. So here we have a sum over all pairs of value assignments of the product over clauses of this expectation. And the first thing to observe is that since these things are also identically distributed, we just get the mth power of whatever that is. And then the next thing to observe is basically all that this expectation is saying is fix sigma, fix tau, draw a single random constraint, and tell me what is the expected value of this function. And it's not hard to imagine that since we draw the variables in each constraint completely at random, there is some kind of very simple parameter that measures the interaction between sigma and tau. So effectively, if you just give me a small matrix, so let's say that we're working with constraints in which the domain size is D, if you give me a small D by D matrix, which tells me how many variables receive each value in sigma and the corresponding value in tau. So Dij tells me there's that many variables that take the value I in sigma and the value j in tau. I can write this down. So the point is this is a collapse from the original variable space of size n to a constant size space. And then we can now rewrite this sum in terms of this expression. So we reorganize the sum by splitting into equivalence classes, each class corresponding to some particular value of the overlap parameter. And then we have to say, okay, we sum over the overlap parameter, how many pairs of assignments, of value assignments are with this particular overlap parameter, and what is the value that they get in the correlation factor. And what's nice is that now this sum has polynomially many terms of exponentially large quantities, so essentially it is dominated by the behavior of the largest term. So in the end, to estimate the second moment of x, we basically have to solve what a physicist will call an entropy-energy trade-off. So when the problem is under constraint, this term is 0. And of course, the maximum corresponds to uncorrelated pairs of value assignments. This is what maximizes entropy. And it's not hard to see that if this is true at 0, it will also remain true for some perhaps very small value of r just by continuity. And then what happens is as you increase r, at some point you get a phase transition, where by phase transition I mean that there is a very large displacement in the locus of the maximizer. So it used to be that the maximizer corresponded to uncorrelated pairs, and then at some critical value of r, it turns out that it's a good idea to invest in this term, and now the maximum shifts very far away. And if you take sort of a statistical physics interpretation of this, it says that, look, below this critical value of r, if you drew a random pair of solutions for your problem, they would be uncorrelated, but above it, in the typical configuration, they will be very, very highly correlated. And as we will see, this phenomenon has some kind of a strong algorithmic shadow. Yes?
Excuse me, you haven't defined A.
A is sort of problem dependent, but in general, it is, if you're working with constraint satisfaction problems in which the domain of each variable has size d, yes, it is simply a d by d matrix which tells me what fraction of variables receives, like entry ij tells me what fraction of variables takes value I in sigma and j in tau. And that object is enough. This collapse basically from the full variable space to just something which is of finite, which is just the size of the domain. I'll do a couple of examples, and I think this might make it clear. So, like I said, as you can imagine, the second moment method succeeds if and only if the dominant contribution to the second moment comes from uncorrelated pairs, because uncorrelated pairs are essentially of the same order as the square of the expectation. So if we look, for example, at applying this method to not all equal k-sat, which, like I said, you can think of it also as the problem of finding complementary pairs of satisfying truth assignments. The matrix would be 2 by 2. How many bits are 0, 0, 0, 1, 1, 0, 1, 1. But it turns out because the problem is symmetric, all you really need is just the Hamming distance between sigma and tau. And then, this joint expectation over a simple constraint is just what's the probability that if you fix sigma and tau that have distance alpha times n, what's the probability they both satisfy a single random clause? And the answer is 1. Minus the probability that either one of them fails to satisfy it, which is just 2 to the 1 minus k times 2, plus the probability that one of them fails and the other one of them fails conditional on that. And the only thing that's really worth noticing here is that this function is symmetric in 0, 1. Okay? Which says the intuitively obvious that whether you're very, very close to someone or very, very far from someone is basically the same thing in this particular problem. So let me now try to show you a small animation. So the horizontal axis is alpha, the normalized Hamming distance between pairs of solutions. And the vertical axis is a number such that if you raise this to the power n, it tells you how many pairs of solutions are that have this normalized distance. So this is the beginning of time before we have added any constraints. And as you can see, this is exactly the entropy function. Okay? So the dominant contribution is just the peak term, which says everything is a solution. So if you pick two random solutions, there's going to be a distance n over 2. That's all. Okay? But then as we add constraints, the shape of this distribution changes. This is as we're increasing R. And now the dominant contribution is still uncorrelated. 1/2 is still the global maximum. But then at some point, these two side peaks will overtake. And that's where the second moment method breaks down. Okay? So this is a typical application of the second moment method in this context. Okay? I'll just do one more, perhaps in a bit less detail. If you want to look at the random graph gay coloring problem, in this case, it turns out that it's a bit helpful to do a filtration of the set of solutions. So rather than looking at all valid K colorings, we look at K colorings that are perfectly balanced. So each color class has exactly n over K vertices. So what this means is that this overlap matrix A is K by K, just the different colors. You tell me what fraction of vertices are in each color class. And it's doubly stochastic by virtue of the fact that our colorings are perfectly balanced. Yes? And when I say doubly stochastic, I mean scaled by times 1 over K. So this is the overlap matrix. Its entropy is exactly what you would think. There is nothing, algebraic about it. And then the correlation function for this problem is just this quantity, which since we're close to 1, you can roughly think of it as just the sum of square entries of the matrix. Okay? And the set that we're working over, is the sense of all doubly stochastic matrices. So we're basically working over the Birkhoff polytope. Okay, so this is a polytope in K minus 1 squared dimensional space. The vertices are all the permutation matrices. So when the graph has no edges, there are no constraints. The maximizer is determined purely by entropy, and it's at the center of the polytope. But as we increase the density of the graph, remember, we want to maximize the sum of these two terms, where this one gets multiplied by the graph density. As we increase this, we have to start paying attention to this term. And this term is happiest at the corners of the polytope. Okay? You would like to have the mass in the matrix be as concentrated as possible. Given that this is a doubly stochastic matrix, the best you can hope is basically for a permutation matrix. So you have two forces. One wants to spread the mass as evenly as possible. The other force wants to actually make it as uneven as possible. And at some point, you have to break this symmetry. So for a while, you can keep increasing R, and entropy wins, which means that typical K colorings in the graph are uncorrelated. But then there is a critical density in which this stops being true, and the locus of the maximizer jumps from the center of the polytope to somewhere very near the corners. Yes?
Is there a reason to see why this value, they are picked so that the two terms are equal, matches often what's given by the union bound on the other side? That's the result you described seem to show.
That's right.
This argument gets you
That's
very
right.
close to what the union bound gives on the other side. Why?
One, I think I only have a sideways answer to your question. I think I only have a sideways answer to your question. Yeah? So like I said in the beginning, each clause, let's say in satisfiability or in coloring, but let's say in satisfiability, yes? It's a cube of codimension K. Rather than thinking of this as a cube of codimension K, basically sort of, blow on it and make it become a cloud of an equal number of points, but a random cloud of size 2 to the n minus K. And imagine that these were your constraints, yes? If that were the case, then the bound you would get would be exactly the first moment bound, okay? So in a way, this is telling you that packing the constraint in this nice cube speeds up the rate at which you're covering things. It's like a coupon collector problem where you're getting coupons en masse, but not a lot because of the high dimensionality. I don't have a better answer than this. Okay? So I was about to get to this. So the truth of the matter is, even now, we don't know exactly when this overtakes. So when symmetry breaks, we don't know how it happens. We can prove bounds, and the bounds are good enough to show the result I mentioned. But there is a beautiful conjecture by Chris Moore. And essentially, the conjecture says that, look, when there are no edges in the graph, the maximizer is at the center of the polytope. Fine. If you imagine putting all edges in, then the maximizer is definitely going to be a vertex. Okay? And his conjecture is that if you take a line that connects the center with any vertex, when symmetry breaks, the new maximum is on that line, but somewhere very close to a vertex. In other words, that symmetry breaks in the simplest possible way, meaning that the new maximizer is just a linear combination of the flat matrix and the identity. Okay? So, yes?
I guess a different way to ask the question is, do you have some characterization of constraint satisfaction problems for which this would match? This is well defined, but the union bound
Yes.
is well defined when they meet. When the
So-
bound meet, well, close to meet. Yeah, I understand. Yeah, when they're really close.
I don't, but I think the reason is sort of a noble reason. We've been trying to characterize the problems for which you get it exactly. So for which this argument and the upper bound coincide precisely. And we think we have some good ideas about this. I will talk about this near the end of the talk. The two being really close, I think will fall out of some generic proof that says that basically for every constraint satisfaction problem, this is true. Precisely because of this high-level geometric argument I gave, that packing the constraints into cubes doesn't help much. Yes?
But for random graphs, they can't ever exactly meet, can they?
That's right. For random graphs are not such a problem.
What I meant is that the
That's right.
difference between them is little low of the value.
Yeah, but a little low of what?
The value. The value of the R.
But in terms of what?
So for example, like for graph coloring, the upper bound is something like k log k minus log k minus log k, yes?
Coloring, you have a natural parameter k
Yes.
that you're increasing, so you can talk about
The density. We have a natural graph parameter, the average degree.
For generic CSPs, it's not clear how to have a sequence of increasing linearity or increasing.
True, but I tend to think about this point-wise. What I'm interested in is just the increase in the density of the constraints, yes? So this is point-wise in some particular constraint set. Okay? So like I said, the conjecture for this, and this is, if anybody's interested, this is a nice problem to work on. It's a very simple, to state at least, problem. You take the Birkhoff polytope, you have two things that are fighting. One is entropy pushing towards the center. The other one, you can think of it as just the L2 norm, sum of squares pushing towards the outside. Where does the maximum lie whenever you have to do such an optimization? One thing that we sort of have a sketch of a proof for is that symmetry can only break in interesting ways, meaning either it breaks in the simple way suggested by Chris, or in fact it is fractal, so you get a recursive structure for the maximizer. Now, all this was introduction, I guess. So what I've been working now for a while is, why is there this gap between the largest density for which algorithms work and the largest density for which we can prove that that solutions exist? And it turns out there is a parallel, at least it used to be parallel for me, universe of physicists who actually have incredibly sophisticated thoughts on this question. And I think their thinking kind of goes like this. So on the horizontal axis, I'm going to have the density of the constraint satisfaction problem. And think of this as some kind of an indicator in a video that plays. So in the beginning, when there's no constraints, everything is a solution. And the set of solutions is typically some kind of nice convex set. Where by convex, what I mean is if you take two elements in the set, there is a shortest path connecting them that's fully in the set. And then you start adding constraints, and the set remains nice for a while, but then suddenly it shatters. Okay? And it goes from being this nice sort of puffball to something that I call an error-correcting code with fuzz. So you get a collection of exponentially many such balls that are linearly far apart from each other. So if the nearest 2 points between them have distance omega n. And then after this shattering happens, if you're familiar with the notion of an energy landscape, you can think of this as the valleys of the energy landscape. Okay? So it used to be that you lived in a nice planet where there was this just single massive basin of attraction. Okay? And then poof, what happens, there's some kind of tectonic shift, and you get lots of mountains and valleys, and these are the bottom of the valleys. And then as you add constraints, those vanish, and at some point, they're all gone, and there are no more solutions. So this is the picture that physicists put forward a long time ago. And this picture is not just qualitative, it's actually also quantitative. They make explicit predictions about the location of this point for each problem, and the methods by which they make these predictions don't seem to be algorithmic at all. So some of them in the old days used to involve something known as the replica method. Now they do something which is slightly more algorithmic that they call the cavity method. But in any case, what I think is really remarkable is that their prediction is that this separation from nice energy landscape to ugly energy landscape coincides with the algorithmic barriers that we've been facing. So for each problem, if you look at the largest density for which we can show algorithms that can find solution in polynomial time, this actually coincides with the point that physicists say, you know what, there's actually a phase transition in the geometry of this set. Yes?
So just to clarify, the second moment still works here?
Yes, the second moment works up to here.
Because there are many clusters that are uncoupled?
Yes, exactly. So the second moment survives this phenomenon. In some sense, this phenomenon is about long-range correlation. The second moment cannot feel those, precisely because this overlap parameter that I described is actually a finite parameter. Okay? So that's right. So we can prove that solutions exist, and then physicists say, but this happens. And I think in my mind, very interestingly, this point is the same, and it's derived from two completely different ways. So the main, I guess, contribution of this new work is to show that this prediction made, prediction is, Remy, is that acceptable? Or? There's a physicist in the audience. Okay, this, I don't know what to call it. This is always a struggle. This extremely nice idea by physicists is also mathematically rigorous. So just in order to be able to formulate the theorem, I just need a few definitions, but I think these are the only definitions in the talk, and I think they're fairly natural. So we're working with n variables, and they all have the same domain D, and sort of adopting a bit of the physicist's language, we will say that we have an energy function which maps configurations of the variables to the integers, and all that simply does is it counts the number of violated constraints. So in particular, a value assignment is a solution if and only if it has energy 0. Now, we will say that two solutions are adjacent if their Hamming distance is 1. So a cluster is going to be a connected component of solutions under this notion of adjacency. And it turns out that for technical reasons, it's helpful to introduce this notion of a region to be a non-empty union of clusters, okay? But I promise you that I will never sort of abuse these definitions. All I will really use this notion of a region for is to agglomerate clusters that are, really, really close together. So in your brain, you should just replace the word cluster with the word region, and I promise I'm not cheating. And finally, if you give me any particular path between 2 points in this energy landscape, I will say that the height of the path is just the maximum value of the energy function. Because it's like if you want to travel between two places, you know, how high up a pass do you have to go in order to be able to do it in the winter? So with these definitions in place, let me say that the set of solutions of an instance of a random constraint satisfaction problem is shattered if there exist exponentially many disjoint regions, which of course implies that there are exponentially many disjoint clusters. And none of these regions is particularly significant. That is, every one of them contains only an exponentially small fraction of all solutions. So it's not like you have a big rock and there's, you know, small pieces of dust floating around. And then every single pair of regions has Hamming distance omega n. And this is really where we use the discrepancy between regions and clusters. Sometimes you can have clusters that are very, very close together, that sort of by accident, in some sense, got split. And then finally, and in some sense most importantly, if you look at any path between two distinct regions, not only is it linearly long, but at some point it has to go linearly high up. Okay? So if you have some kind of an algorithm that is trying to find solutions to the problems by trying to drive the energy function down, like a random walk type algorithm or simulated annealing, or in fact most things that we've tried to use, at some point you'll have to be very risky and very generous and accept the fact that you will be making moves that take you very, very far away from where you want to be. So now with this definition and picture, here is one theorem about graph coloring, and basically says, well, up to 1/2 times k log k, a very simple algorithm finds solutions. Above k log k, there are no solutions. And in between, there are solutions, but the energy landscape is shattered. Okay? So you can interpret that perhaps as the natural mountain or barrier that we have to overcome if we actually are to find algorithms that run in polynomial time and beat this one half factor. And then for satisfiability, it's exactly the same deal. We know that solutions don't exist above density 2 to the k log 2. We know that there is an algorithm. It used to be 2 to the k over k times a constant. Now it's 2 to the k over k times log k. It works up to this. And for everything in between, the space of solutions is shattered. It looks, like I said, like an error-correcting code with fuzz. Yes?
These heights, so do you know if like below that barrier it's not shattered?
I don't understand the question.
Is this the only region in which it's shattered? Or shattered?
Well, above here there are no solutions, so there's nothing to discuss. And down here I will give, in the next slide, the theorem that suggests that it's not shattered. Yes? I didn't define the complement of not shattered, so I'll give an implicit definition now. And what's, I guess, one thing that I like is that if you look at the proofs of these theorems, they're fairly generic. Essentially the same proof goes through for a bunch of different problems. The only point where you have to do problem-specific work is in determining the exact constants. So now, let me say that if you give me an instance and the solution in that instance, I'll say that a particular variable is frozen in that solution in this instance if the following is true. If you attempt to change that variable and make it take some different value, you also have to change a linear number of other variables. Okay? So this single change propagates dramatically. A different way of saying it is that, you know, if you move to this point, then all solutions become very, very away. And contrast this with, in some sense, the best definition we could have in the opposite direction, which is to say that a variable is loose in a solution if you can change it to any value that you like, okay? And that will only cause you to modify little o of n variables. It won't propagate. And in fact, you can actually strengthen this to be big O of log n. Okay? So effectively, I think you can imagine, for example, a solution or a set of solutions in which every variable is loose. Effectively, this is a convexity, a sphericity statement. It basically says you can do whatever you like. Okay, you only have long-distance correlations between the constraints. And that's what we prove, that in the ball regime, which I mean below the shattering point that I described, every single variable is loose. On the other hand, in the shattered regime, nearly all variables are frozen. So when I drew the schematic earlier, I said you used to go from one nice big cluster to many small little clusters. And I guess there was more truth in that drawing than I actually said at the time, meaning that if you look at these clusters, they really look like balls. They don't look like wispy clouds, by which I mean that there is a constant fraction of the variables, significant, like 80%, that are completely frozen, and they form the core of the cluster. And then the other 20% of the variable is essentially fluff. Okay, they have very short range correlations. So if you're in that cluster and you attempt to change any one of the frozen variables, you're dead. You have to go to a different cluster. You can only muck around with that 20% of variables that are very loosely connected to each other. So I don't know, at least for me, this idea that in order to find solutions, I have to solve an error correction problem, except that, you know, when I start off, I'm not near necessarily a solution. I'm in a random place. Suggests that life for algorithms in this world might be quite hard. There's a graphical analogy that I don't know if it is correct, but at least I find it satisfying. So think of an egg crate, okay, that you use to put eggs in. And think you have each egg, I don't know what you call it, egg case, I guess, every single one. At the bottom of it is a solution to your CSP. Okay, that's the lowest energy point. And then in the sides of the rim, those act as an attractive basin. Okay? So for example, in error-corrected codes, what you want to transmit is at the bottom, and then the channel perturbs you, but if the signal-to-noise ratio is not very high, you will just go to the side of the rim, and then a fairly naive algorithm will allow you to go back down. Okay? At least if you do some kind of modern LDPC iterative-style decoding. And now, I guess the question is, if you have an egg crate, if you look at the point where 4 little baskets meet, at the top there is this flat area in which you get no gradient. Okay? And if you start there, you don't really know where to go. So it seems that in this landscape, a very important quantity is the ratio between the volume of the cube that belongs to attractive regions versus the volume of these badlands in which you essentially have no gradient towards anywhere. I'd like to give some idea of how we prove these results, not for the sake of the proofs themselves, but because there is a technical enablement for these proofs that I think might be useful in other contexts. So let me first describe a weaker result that we had before this, and say that, let's say in a random, or in a general, in a KCNF formula, let me say that a satisfying truth assignment sigma is rigid if more than 90% of the variables are frozen. Okay? And then here's a theorem. For all k greater or equal to 8 or something, if the density is in the last 1/5 of the satisfiable regime, then with high probability, every single satisfying assignment is rigid. Okay? So to prove this, here's what you do. We'll just do a union bound, and we'll say the probability that there is a bad value assignment is just the sum over all value assignments of the probability that sigma is satisfying and not rigid, which I just used Bayes' rule to write as the probability that it's satisfying times the probability that sigma is not rigid given that it's satisfying. Now, this is really easy. This is just this quantity. And then all truth assignments have the same behavior in this regard, so this gives me this. So remember, this is just the expected number, really, of satisfying truth assignments. And now I'm left with this term, which is what's the probability, let's say, that a particular assignment, all zeros, is not rigid, given that it is satisfying. And what's nice about this is that conditioning on 0 being satisfying essentially gives me a product probability space. I go into my bag of all clauses, and I remove those n choose k clauses that disagree with all zeros. And then I sample uniformly from the rest. Okay? So this is a very nice probability space to work with. And what I have to capture now is, what is this probability? And to capture this probability, we actually get a lot of help from physics. Physicists have a heuristic algorithm for determining the projection of any particular component of solutions in a KCNF. In other words, they will, if you give them a satisfying assignment, they will return a string of length n that contains 0, 1, star. The meaning being, if they return a 0 or a 1, then for sure, this particular variable is always 0 or always 1, whatever they say in that component. If they return a star, it might or not might be the case that this variable is frozen. So to get the proof, we have to compute, like I said, this quantity. And the hard part is that, remember, we want this whole thing to go to 0. This is exponentially big, so we have to get an exponentially small probability, which means that we have to capture sort of the large deviations behavior of this algorithm. And if you do it, I mean, you get the rate function for this. And if you drive the density high enough, this becomes less than 1, and you win. Okay? On the other hand, the phenomenology is that actually most variables are frozen for densities way below 4/5 of the threshold. That the densities are, that the variables become frozen already at basically 2 to the k over k times log k. But we can't quite prove it using this proof, because to compute this quantity, we planted the all zeros formula, the all zeros assignment. Okay, it is not a generic satisfying assignment for which we can say things. Now, on the other hand, if you actually compute this probability and you don't want it to be exponentially small, you do recover this point. Okay? So if you just want a 0-1 law for the probability that all zeros is satisfying given that that it's not rigid given that it's satisfying, you do recover the right place. But of course the problem is that, a planted assignment is not the same thing as a random satisfying assignment. And the object of desire for us really here is the uniform measure over the set of solutions. So when I was a graduate student, my advisor sort of made sure that I understand this point very well. It's very, very important. And it's sort of with great pleasure that a number of years later can sort of prove that my advisor was wrong. And that's the main technical enablement of all these results, which is the fact that actually a planted assignment and a random assignment are essentially the same. Okay? And I will make this statement precise, but I think a more graphical statement is to say, look, generate a random CSP, go to the bottom of a random valley, sit there, take a look around at the scenery, call this picture 1. The other one is pick a random point in the cube, make this the bottom of an artificial valley in the sense that you now draw constraints so that this remains the bottom of a valley. Reach the same number of clauses as before, look up, take a look at the scenery, call this picture 2, and then the theorem is picture 1 equals picture 2. Okay? So here's the proof of this fact, and it's remarkably, in my opinion, remarkably simple. I'll describe it for graph coloring. So think of this really, really big matrix, the columns of which correspond to graphs that have n vertices and m edges. So every possible graph with n vertices and m edges gets represented here. It gets a column of its own. Okay? And then for the columns, let me put all possible k colorings of the vertices of the graph. Where by k colorings, what I mean is k partitions. There's no edges yet. Okay? And one thing to observe is that when you look at the set of all possible k partitions, really what's going to dominate are balanced and very close to balanced partitions, yes? So everything is going to have n over k, every part is going to have size n over k plus minus central limit terms. And then let me put a 1 whenever a particular partition is a valid coloring for that graph. Okay? Is this point clear to everyone? Is this picture clear? Okay. So now, what we're actually interested in is, a random solution, a random k coloring of a random graph, which means you first pick a random column, and then inside that column you pick a random 1. Okay? That's our object of desire. That's what we would like to study. On the other hand, what was easy for us to study and what we know how to do is to plant the coloring, which means we first pick a row, so we first pick a partition of the vertices at random, and then we pick a random graph which is compatible with that partition. That is, among all graphs for which is a solution, we pick one uniformly at random. And as you can imagine, these are two completely different distributions in general. One way to think about it is that graphs that are rich in k colorings, that have many k colorings, are much more likely to appear under the second model. Now, on the other hand, there is a very simple observation that says, look, imagine for a moment that this matrix was a balanced matrix. That is, in every row, you had the same number of 1s, and in every column, you had the same number of 1s. Okay? This would imply that these two probability distributions are completely identical, because what they both do is they pick a uniformly random 1 from the entire matrix. Okay? Well, let's look now at our situation. Effectively, we have row stochasticity. Okay? Pretty much, if you pick a random partition, they're all the same in terms of the number of graphs for which they are solutions. If you think in terms of satisfiability instead of graph coloring, then it's clearly exactly the same. Okay? So the matrix that we have is already row stochastic just by the symmetry of the problems that we consider. Now, on the other hand, what would it mean for this graph to also be column stochastic? It would mean that all instances have the same number of solutions, right? But what is this? This is just a concentration statement about the number of solutions, okay? And I think intuitively, at least, you can be convinced that in order to be able to make these two processes be alike, I don't need this graph to be perfectly balanced. In other words, that's not a very fragile statement. If things are approximately stochastic on the left and approximately stochastic on the top, then I should be able to invert the two distributions with a quality that it's analogous to the amount of concentration that I have and row stochasticity that I have. And this is precisely what we do. I mean, we have shown that solutions exist in random constraint satisfaction problems exactly by a concentration argument, right? That was what the second moment method was about. We proved that essentially for densities almost all the way to the point where no solutions exist anymore, the number of solutions is very, very close to its typical value. In other words, all these columns contain essentially the same number of 1s. And therefore, I can do the inversion. What's nice about the inversion is that now, if I want to study the uniform measure on the set of solutions, which I have absolutely no idea how to access, I can instead simply look for properties of a planted solution. Okay? I literally pick a string, I say this is going to be my solution, now I build the formula around it, and now I can start ask questions, which is how big is its cluster? Okay? But what's nice is I'm not working in a conditional probability space. Okay? I'm just working on a product space that resulted by saying that this is a solution and everything else I just draw uniformly. So now I can start growing the cluster and I can understand everything. Then I can say, okay, is there a gap in the distances between my cluster and the next? And again, you get short proofs of this statement. So pretty much your life becomes very luxurious. And there is, I guess, one more implication of this is that you can use it to build one-way functions. And I'm not necessarily saying that these are good one-way functions, but I'm happy about it, and I'm sure that people in the audience will have a much better sense than me about this. So assume that for random instances of some particular constraint satisfaction problem, it is true that you can establish concentration on the number of solutions. So let's say graph coloring. This is something for which we already know that the number of k colorings in a random graph is the sharply concentrated random variables. So in this sense, and assume further that with some probability, some particular algorithm needs a fair amount of time on a random instance from this distribution. Then what you do is you take something like log n squared independent planted instances. You could just take one and risk being unlucky. So you just take log n squared just to be safe, parallel repetition. And it immediately follows that this ensemble of instances is going to be hard for your algorithm. But what's nice is you know how to solve every one of those instances because you actually planted the solutions. Okay? So this is a way, in some sense, of creating an energy landscape which appears to be very hard to navigate, while at the same time knowing the location of some particular valley. Okay? And the reason, effectively, you can do this is that the effect of pinning some particular location in the cube to being a 0 cannot be felt from far away. Okay? It seems like the walls of the attractor are actually sufficiently steep that you can't sense it until you get really, really close to it. And moreover, you don't even have to be able to prove this property for the set of solutions. It is enough, sorry, I messed this up. What I meant here is, as long as you can prove this for a random variable x, which counts the cardinality of some subset of the set of solutions, then you can plant such objects. So for example, in satisfiability, you can say, well, I'm actually going to plant not a single solution, which for reasons that I don't have time to explain, doesn't actually work because the second moment method doesn't work. So algorithms find those easily. But it turns out that if you plant a complementary pair of solutions, okay, so you pick a sigma, and then you say, I'm only going to take clauses that are compatible with sigma and sigma prime. Because for such pairs of solutions, the second moment method goes through, you can do this inversion, and the resulting formulas are actually extremely hard. In a certain sense, from what a physicist would say, is that the local fields cancel each other. Okay? So if you only plant one, you get a lot of attraction towards it, but if you plant two, they kind of negate each other and algorithms get lost. That's the slide. So this is what I meant to say. I call these things keys. And so to conclude, there is ongoing work. One of the things that follows immediately from this, the roughness of the landscape is that pretty much any kind of algorithm that respects detailed balance, so any kind of Markov chain that we know, we typically know how to look like, is not going to have a chance of reaching equilibrium in polynomial time in the shattered regime. But then there are random walk type algorithms like walksat, which are essentially out of equilibrium algorithms, But we still don't think that they can make it, but we can't necessarily prove it yet, so this is active work. Another thing which I believe is quite interesting is to prove that this idea that you go from a single cluster to exponentially many clusters to nothing is really uniform and problem independent. And I think that there is very strong evidence that any kind of proof of that nature will actually use a lot of the machinery that Ryan talked about yesterday. And the reason is that if you remember this animation that I showed you, this animation is simply the result of taking the entropy function and multiplying it by a correlation function, the power of which we keep increasing. Well, it turns out that you can decompose the evolution of this video in terms of the Fourier analysis of that correlation function, okay? And then everything becomes quite generic. You don't have to make it problem specific. So you can express things like, for example, the derivative of this function at the points that you really care about, at 1/2 and at 1, you can express it in terms of the influence of a single constraint. In other words, how many edges in the cube are actually present between solutions. So in that sense, parity is really special because in parity, as soon as you change any bit, you have to change another one. There is not a single edge in the cube that survives, okay? Another way of saying the same thing is, well, you have this bipartite expander, you have a solution, now you change a single bit, and you're working with a CSP which has a property that in any particular constraint, if you flip one bit, you have to flip at least one more. Well, what do you expect to happen? Okay, these things will propagate, and probably the nearest solution that you get from changing a single bit is going to be linearly far away. So this is what gives us good error-correcting codes, but it turns out we would like to also get a Fourier theoretic characterization of the same thing. And it turns out there's other problems that have the same property. So one thing that at least I am hoping to get out of this analysis is some kind of proof that says that if you want to build good error-correcting codes, using XOR gates, as we've been doing now for a long time, is actually best possible, okay? That you can't build good error-correcting codes using something better than this. And then finally, there is this question, which I think is what ties perhaps my talk most to this workshop, but it's also perhaps the most ambitious bit of it, is in everything I talked about random instances, okay? But the only place in which I actually use the randomness is in building this bipartite expander. And then if you actually look at the proofs that we have for most things, but not for everything, they're actually very soft arguments. They don't necessarily use the independence of things. And so we're working actively on trying to make them softer and softer and softer so that you never use independence, you never use the fact that the constraints are IID, and you try to use softer ingredients like expansion. So in my mind, it would be very, very nice if we could replace random bipartite graphs with expanders, because then we can use explicit constructions of expanders such that with few parameters, we can actually have full control of the energy landscape ourselves. That's it. Thank you.
So you would remove randomness for what, or what would you construct non-randomly?
If I remove randomness,
So you said that by replacing expanders,
no, I don't want to replace expanders.
by making them explicit, but I somehow missed what you would consider.
If it is an explicit construction of expanders, then perhaps I have some chance of getting the fact that the zeros of the function that results perhaps has some periodic structure that I can now start to exploit algebraically. In other words, the algebra that I used to create the expander might now be reflected in the high-dimensional space. I mean, this is still very far away, right? Step one would be to take all that stuff and make it in some sense non-random, non-probabilistic.
Yeah, but what object would you like to make
the instance would be deterministically constructed. The instance.
Like what you know for XOR, that the moment it is an expander, it is shattering.
But it's actually not hard to come up with specific CSPs with shattered solution spaces, right?
Yes, that's right.
If you take an error correcting code.
Sure.
you map it to a CSP.
Sure.
So you want
To be sort of completely generic and soft and universal, yeah. So basically, to just say, unless your constraint is completely brain dead, like the constant function or something, if you put it on the left and then you put an expander in the middle, that's what happens. Boom. That's it. So completely plug and play. Yes.
So what happens if you apply this whole philosophy to linear equations? Linear equations are solvable for any parameter R. They do generate error correcting code, obviously.
Yes, that's right. So this is a very pointed it's a very pointed question. It is true that we know how to solve linear equations, but we only know how to do it in an algebraic sense. Okay, we basically have to use Gaussian elimination. If you take any of the algorithms that people have developed to solve satisfiability, and you try to use those to solve linear equations, they fail miserably. And the reason they fail is because they don't understand the global structure that you have from linearity, which is precisely what you exploit with Gaussian elimination.
So that suggests that we should try algebraic techniques too.
Good luck. Sure, yes. You should try algebraic techniques.
More questions? Well,
The survey propagation algorithm is another one of these local ones.
Why don't you ask the guy behind you? Short answer is I don't believe survey propagation works. And we can essentially prove this at this point. There's one distinction. There is one sense in which survey propagation might very well work above the shattering point, but work not in finding solutions, but in actually telling you what is the marginal probability distribution of each variable over the uniform measure. Okay? So if you give it a formula, and then for each variable, it will tell you this variable is 60% true, 40% false. Okay? And it will do that for every variable. And now, of course, you can say, oh, great, self-reducibility, I will instantiate and redo, right? And the problem is that if you try to apply self-reducibility to this, the rate at which you are killing clusters and the rate at which the landscape becomes ugly is such that after a while, you cannot do this marginalization, even with survey propagation or belief propagation. So at the end of the day, you cannot use it to find a solution.
Don't you expect that throughout most of the shattering regime, the answer is just 50-50?
It depends on the problem. So the short answer is no, okay? Because remember that variables have finite degree. So a variable that appears 10 times positive and 3 times negative, it's reasonable to believe that it's going to be biased, yes? Of course, for a problem like, coloring random regular graphs, yes, you get absolutely no information. Everything is completely flat, yes? And even after you start instantiating colors, it remains flat for a while. But at some point, you actually start getting useful information, but not enough to find solutions.